A spark gap transmitter is a device that generates radio frequency electromagnetic waves using a spark gap. Spark gap transmitters were the first devices to demonstrate practical radio transmission, and were the standard technology for the first 3 decades of radio. Later, more efficient transmitters were developed based on rotary machines like the high-speed Alexanderson alternators and the static pulse arc generators. Most operators, however, still preferred spark transmitters because of their uncomplicated design and because the carrier stopped when the telegraph key was released, which let the operator listen through for a reply. With other types of transmitter, the carrier could not be controlled so easily, and they required elaborate measures to modulate the carrier and to prevent transmitter leakage from desensitizing the receiver. After World War I, greatly improved transmitters based on vacuum tubes became available, which overcame these problems, and by the late 1920s the only spark transmitters still in regular operation were legacy installations on naval vessels. Even when vacuum tube-based transmitters had been installed, many vessels retained their crude but reliable spark transmitters as an emergency backup. However, by 1940, the technology was no longer used for communication. Use of the spark gap transmitter led to many radio operators being nicknamed sparks long after they ceased using spark transmitters. Even today, the German verb funken, literally, to spark, also means to send a radio message or signal. History. The effects of sparks causing unexplained action at a distance, such as inducing sparks in nearby devices, had been noticed by scientists and experimenters well before the invention of radio, with extensive experiments being conducted by Joseph Henry, Thomas Edison and David Edward Hughes. No other theory at hand to explain the phenomenon, it was usually written off as electromagnetic induction. In 1886, after noticing unusual induced sparking in a Reese spiral, physicist Heinrich Hertz concluded this phenomenon could be used to scientifically verify James Clerk Maxwell predictions on electromagnetism. Hertz used a tuned spark gap transmitter and a tuned spark gap detector located a few meters away. In a series of UHF experiments, Hertz verified that electromagnetic waves were being produced by the transmitter. When the transmitter sparked, small sparks also appeared across the receiver's spark gap, which could be seen under a microscope. Many experimenters used the spark gap setup to further investigate the new Hertzian wave phenomenon, including Oliver Lodge and other Maxwellian investigators. The Serbian-American engineer Nikola Tesla proposed methods to synchronize sparks with the peak output of an alternator, which he patented in 1896, while pursuing a wireless lighting and power distribution system based on his own conduction ether theories. The Italian inventor Guglielmo Marconi used a spark gap transmitter in his experiments to develop the radio phenomenon into a wireless telegraphy system in the early 1890s. In 1895 he succeeded in transmitting over a distance of 1¼ miles. His first transmitter consisted of an induction coil connected between a wire antenna and ground, with a spark gap across it. Every time the induction coil pulsed, the antenna was momentarily charged up to tens of thousands of volts until the spark gap started to arc over. This acted as a switch, essentially connecting the charged antenna to ground and producing a brief burst of electromagnetic radiation. While the various early systems of spark transmitters worked well enough to prove the concept of wireless telegraphy, the primitive spark gap assemblies used had some severe shortcomings. The biggest problem was that the maximum power that could be transmitted was directly determined by how much electrical charge the antenna could hold. Because the capacitance of practical antennas is quite small, the only way to get a reasonable power output was to charge it up to very high voltages. However, this made transmission impossible in rainy or even damp conditions. Also, it necessitated a quite wide spark gap, with a very high electrical resistance. with the result that most of the electrical energy was used simply to heat up to the air in the spark gap. Another problem with the spark transmitter was a result of the shape of the waveform produced by each burst of electromagnetic radiation. These transmitters radiated an extremely dirty, wide-band signal that could greatly interfere with transmissions on nearby frequencies. Receiving sets relatively close to such a transmitter had entire sections of a band masked by this wideband noise. Despite these flaws, Marconi was able to generate sufficient interest from the British Admiralty in these originally crude systems to eventually finance the development of a commercial wireless telegraph service between the United States and Europe using vastly improved equipment. Reginald Fessenden's first attempts to transmit voice employed a spark transmitter operating at approximately 10,000 sparks a second. To modulate this transmitter, he inserted a carbon microphone in series with the supply lead. He experienced great difficulty in achieving intelligible sound. At least one high-powered audio transmitter used water cooling for the microphone. In 1905, a state-of-the-art spark gap transmitter generated a signal having a wavelength between 250 meters and 550 meters. 600 meters became the international distress frequency. The receivers were simple unamplified magnetic detectors or electrolytic detectors. This later gave way to the famous and more sensitive galena crystal sets. Tuners were primitive or non-existent. Early amateur radio operators built low-power spark gap transmitters using the spark coil from Ford Model T automobiles. But a typical commercial station in 1916 might include a half-a-kilowatt transformer that supplied 14,000 volts, an 8-section capacitor, and a rotary gap capable of handling a peak current of several hundred amperes. Shipboard installations usually used a DC motor to drive an alternator whose AC output was then stepped up to 10,000–14,000 volts by a transformer. This was a very convenient arrangement, since the signal could be easily modulated by simply connecting a relay between the relatively low-voltage alternator output and the transformer's primary winding, and activating it with the Morse key. Spark gap transmitters generate fairly broad-band signals. As the more efficient transmission mode of continuous waves became easier to produce and band crowding and interference worsened, spark gap transmitters and damped waves were legislated off the new shorter wavelengths by international treaty, and replaced by pulse and arc converters and high-frequency alternators, which developed a sharply defined transmitter frequency. These approaches later yielded to vacuum tube technology and the electric age of radio ended. Long after operators no longer used spark gap transmitters for communications, the military used them for radio jamming. As late as 1955, a Japanese radio-controlled toy bus used a spark transmitter and coherer receiver. The spark was visible behind a sheet of blue transparent plastic. Spark gap oscillators are still used to generate high-frequency high-voltage to initiate welding arcs in gas tungsten arc welding. Powerful spark gap pulse generators are still used to simulate EMPs. Most high-power gas discharge street lamps still use modified spark transmitters as switch-on igniters. Operation. The function of the spark gap is to initially present a high resistance to the circuit so that the C1 capacitor is allowed to charge. When the breakdown voltage of the gap is reached, the air in the gap ionizes. The resistance across the gap is dramatically lower and a current pulse flows across the arc to the rest of the circuit. The gap is set so that the discharge coincides with a maximum or near maximum of charge in C1, and it is as if a high-speed switch is turned on at just the right moment to allow the C1 capacitor to discharge its stored energy into the other circuit elements. This pulse of energy is rapidly exchanged back and forth between the C and L elements and takes the form of a damped oscillation at a radio frequency. The back-and-forth exchange of energy is in the form of an alternating current and voltage wave with much of the energy flowing out to the antenna. These waves are called damped waves because the wave tends to die out or dampen out between discharges of the spark gap, as opposed to modern continuous waves, which don't die out, because the damped waves are a train of regularly spaced radio frequency triangle waves that occur at an audio rate. Early crystal, magnetic and Fleming valve detectors heard them as a musical note, rich in harmonics, making it easy for the human ear to copy messages and identify stations by their unique sound, even under adverse conditions. The exchange of energy in this kind of oscillator occurs at a rate or frequency determined by the resonant frequency of its tank circuit, which is composed of the combined capacitance of C1 and C2 and the inductance of L, famously known as an LC circuit. Capacitance of C2 was generally small and generally not shown in most diagrams. C2 represents the stray circuit capacitance, but C1 was relatively huge both in size and capacity, so that it could store the large amount of high-voltage energy necessary for high-power transmission. Some installations had whole buildings devoted to the C1 capacitor. The inductance coils were relatively small so that the entire circuit could resonate at a reasonably high frequency, given the large value of C1. Frequencies much above 1 MHz were impractical, because L could not get electrically smaller and not enough energy could be stored in a small C1, though a small C1 would have been necessary because of the resonance characteristics of shortwave frequencies. In addition to the size and robustness of the oscillator components, the lower frequency components were likewise robust. This is because a very large induced EMF occurs when the spark is struck, causing a strain on the insulation in the primary transformer. To overcome this, the construction of even low power sets was very solid, and a radio frequency choke coil or a resistor was necessary to protect the transformer or induction coil. The telegraph key many times had to carry large currents and high voltages, and so it also was generally quite robust too. Though ubiquitous in early radio, the spark gap transmitter was finally doomed by its extremely broad frequency spectrum and damped wave output. Damped waves were excellent for radio telegraph with early radio detectors, but are very wasteful of bandwidth. This limited the number of stations that could effectively use a band, because of the interference. Also, wide bandwidth meant the transmitter spread useful intelligence over a large spectrum, and only a fraction of the transmit power was useful for communications. Finally, the damped wave is already a form of amplitude modulation and cannot be further modulated for voice with any intelligibility. Only the continuous wave oscillators made possible by vacuum tube technology could provide high frequency and beyond, and only their advent made efficient radio telegraph and voice data transmissions possible. Spark gaps. A simple spark gap consists of two conducting electrodes separated by a gap immersed within a gas. When a sufficiently high voltage is applied, a spark bridges the gap, ionizing the gas and drastically reducing its electrical resistance. An electric current then flows until the path of ionized gas is broken or the current is reduced below a minimum value called the holding current. This usually occurs when the voltage across the gap drops sufficiently, but the process may also be assisted by cooling the spark channel or by physically separating the electrodes. This breaks the conductive filament of ionized gas, allowing the capacitor to recharge, and permitting the recharging-discharging cycle to repeat. The action of ionizing the gas is quite sudden and violent, and it creates a sharp sound. The noise from the spark mechanism, especially from the higher-powered transmitters, was so loud that it could seriously interfere with the operator's ability to receive messages after transmitting. Higher-powered spark gap mechanisms were isolated from the operator's station in an insulated space called the silent room, which, when the radio was transmitting, was anything but silent inside. The spark gap also produces light and heat. Quenching the arc. Quenching refers to the act of extinguishing the previously established arc within the spark gap. This is considerably more difficult than initiating spark breakdown in the gap. As transmitter power was increased, the problem of quenching arose. A cold, non-firing spark gap contains no ionized gases. Once the voltage across the gap reaches its breakdown voltage, gas molecules in the gap are very quickly ionized along a path, creating a hot electric arc, or plasma, that consists of large numbers of ions and free electrons between the electrodes. The arc also heats part of the electrodes to incandescence. The incandescent regions contribute free electrons via thermionic emission, and metal vapor. The mixture of ions and free electrons in the plasma is highly conductive, resulting in a sharp drop in the gap's electrical resistance. This highly conductive arc supports efficient tank circuit oscillations. However, the oscillating current also sustains the arc, and until it can be extinguished, the tank capacitor cannot be recharged for the next pulse. Several methods were applied to quench the arc. Jets of air that cool, stretch, and literally blow out the plasma. Multiplate discharger of MaxWien to cool the arcs in medium-power spark sets, known as the whistling spark, for its distinctive signal. Using a different gas, such as hydrogen, that quenches more efficiently by providing more effective electrode cooling. A magnetic field oriented at right angles to the gap to stretch and cool the arc. Magnetic spark gaps in early radio transmitters varied in construction, depending on the power they had to handle. Some were fairly simple, consisting of one or more fixed gaps connected in series, while others were significantly more complex. Because sparks were quite hot and erosive, electrode wear and cooling were constant problems. Rotary gaps. The need to extinguish arcs in increasingly higher power transmitters led to development of the rotating spark gap. These devices used an alternating current power supply, produced a more regular spark, and could handle more power than conventional static spark gaps. And the inner rotating metal disc typically had a number of studs on its outer edge. A discharge took place when two studs lined up with two outer contacts that carried the high voltage. The resulting arcs rapidly stretched, cooled, and broke as the disc rotated. Rotary gaps operated in two modes: synchronous and asynchronous. A synchronous gap was driven by a synchronous AC motor so that it ran at a fixed speed, and the gap fired in direct relation to the waveform of the AC supply that recharged the tank capacitor. The operator changed the point in the waveform where the gaps were closest by adjusting the rotor position on the motor shaft relative to the stator's studs. By properly adjusting the synchronous gap, it was possible to have the gap fire only at the voltage peaks of the input current. This technique made the tank circuit fire only at successive voltage peaks, thereby delivering maximum energy from the fully charged tank capacitor each time the gap fired. The break rate was thus fixed at twice the incoming power frequency. When properly engineered and adjusted, synchronous spark gap systems delivered the largest amount of power to the antenna. However, electrode wear progressively changed the gap's firing point, so synchronous gaps were somewhat temperamental and difficult to maintain. Asynchronous gaps were considerably more common. In an asynchronous gap, the rotation of the motor had no fixed relationship relative to the incoming AC waveform. Asynchronous gaps worked quite well and were much easier to maintain. By using a larger number of rotating studs or a higher rotational speed, many asynchronous gaps operated at break rates in excess of 400 breaks per second. Since the gap could fire more often than the input waveform could switch polarity, the tank capacitor charged and discharged more rapidly than a synchronous gap. However, each discharge occurred at a different voltage, which was almost always lower than the consistent peak voltage of a synchronous gap. Rotary gaps also altered the tone of the transmitter, since changing either the number of studs or rotational speed changed the spark discharge frequency. This was audible in receivers with detectors that could detect the modulation on the spark signal, which enabled listeners to distinguish between different transmitters that were nominally tuned to the same frequency. A typical high-power multiple spark system used a 9 to 24-inch diameter rotating commutator with 6 to 12 studs per wheel, typically switching several thousand volts. The output of a rotary spark gap transmitter was turned on and off by the operator using a special kind of telegraph key that switched power going to the high-voltage power supply. The key was designed with large contacts to carry the heavy current that flowed into the low-voltage side of the high-voltage transformer. Alternatively, a relay was used to do the actual switching.